So let's discuss gas laws. And what this is just, I'm going to be a little bit of a history lesson of it, I guess, I suppose. Let's talk about thermodynamic variables. So I mentioned already that gases will be the primary focus of any thermodynamics course. In thermodynamics, there are three main variables that you will see and encounter quite a lot, and we will do the same thing here. We will discuss these. Pressure we just discussed. It's how often molecules hit the wall of a container. I just showed you that in that picture with the box. The more they hit, the higher the pressure. We also discussed pressure as sort of a force over an area, the force distribution. Volume is how much space is being occupied. So the gases will occupy, say, a foot cube or a liter. Or maybe if you double the volume, you have more space for them. They will occupy more volume. Moles, we've seen in the other units, is the number of molecules that I have, and the more moles I have, the more mass I have. It's just by definition, the more stuff I have, right? Moles is just a number. A mole is like a dozen. So I'm counting how many molecules I have. And temperature, which we've seen quite a lot. I don't know if we actually ever defined it. It's how much, what's the energy associated with the movement of the molecules. And it's defined as the average kinetic energy of the molecules, kinetic being energy of movement, is how fast they're moving. At absolute zero, at 0 Kelvin or at 0 Rankine, you have no movement from the molecules. They are frozen, literally. They're just not moving, which is why it's so hard, if not impossible, to achieve. I'm not sure. I'm not a theoretical physicist, but I'm pretty sure we have never achieved it, but we've gotten fairly close as humans. It's one of those limits that's, I think, hard to accomplish, because even if you have 0.0 something 1 Kelvin, you will still have some movement and you still have some sort of dynamics going on. So I don't know that we can actually achieve it, but that's basically the idea. The higher the temperature, the more the molecules will be dancing. You think about that as a dance party. The higher temperature, the more energy you're giving the temperature, the molecules to move. All right, so we've talked about compressibility previously, right? I can push down on a gas, or I can pull up. So you can see here in this picture, here, under this condition, the molecules obviously have less volume than in this condition. And what happened here is I pushed on this top. Well, it's not. I didn't push it. Someone pushed it, and so when they pushed it, they squeezed the molecules closer together, and the volume went down. Here it was much larger. So what it worked out, this is Robert Boyle, and this is quite a few hundred years ago, but it's intuitive for us. It wasn't intuitive until then. He just posited that if you were to increase the pressure on a gas, you will decrease its volume. So they are inversely related. Everything else stays constant. If I were to increase the pressure, I would decrease the volume. If I were to decrease the pressure, I would increase the volume. You can see here in this picture of this astronaut, it's the same dude inside, or maybe it's a dudette, I don't really know. And basically, if I have very low pressure, right? So in this scenario, the gas inside the suit will increase and swell. And if I have a high pressure, indicated by the red going up, then the volume of the gas inside will diminish and it will shrivel and it will look this way. Okay, it's the same person inside. They didn't get fat. They didn't eat anything. They're just playing around with pressure. You can see what happens to the volume of the gas. Okay. There is a volume and temperature are also related, and they're actually positively related. So that if you increase the temperature, you increase the volume. If you decrease the temperature, you decrease the volume. And this was posited in the 18th century by a scientist named Charles. Last name, I don't remember his first name. And so if this happens, you can do this yourselves. If you were to blow up a balloon, and tie it up and put that in the freezer, you will see that it will shrivel. Why is that? Again, going back to the idea that molecules are forever hanging out in a dance party. If you were to reduce the energy in the room, they would have less of an energy, be more tired, I guess. They won't move as much. And that's what's happening here. They move less, and so they push on the walls less, and they don't want to expand the balloon as much, and so they reduce in volume. Here, if I were to put the same balloon in boiling water, I am adding energy to them. They're happier, they're more perky, they're running around, and so they will increase the volume of the balloon. Okay, so this is one of those. If you have a third grader cousin or something, and they want to have a science fair project, that's a great one to have them play with. Temperature volume relationship in a balloon. Why not? It's pretty easy to do. Just careful, boiling water is dangerous, right? Avogadro did other things other than the mole stuff. Well, it's still related to moles. But basically, what he posited is pretty intuitive. If I have half the stuff, I will occupy half the volume. If I have double the stuff, I will occupy double the volume. That's pretty obvious, I think. Okay. We could put all that together, the PV and N and T together, and marry all three laws together into something that you doubtless you have not. You've definitely seen this in the past. PV is equal to nRT. This is known as the universal ideal gas law. The R here is the universal gas constant. The ideal gas law, also known as the perfect gas law. This is related to the idea that we're talking about ideal gases or perfect gases. And all of the assumptions that I've shown you so far, they have no volume, they don't interact with one another, etc., etc., etc. These are the ideal gas assumptions. They're not real, but they are close enough. And they give us such an easy to work with formula. And I'll show you some other models of the gas laws that if you take thermodynamics later, you'll see and use them as well. It gets hairy, it gets complicated. If you try to model real gases, it's not this nice at all. And you have to use much more complicated modeling tools to do that. All right. Now, P is pressure, V is volume, N is moles, T is temperature. What's this R? R is known as the universal gas constant. It's also known as a fudge factor. It really is. It's just there to convert units. It's just because it's not, I mean, these things are all linear, but there's some sort of a factor that's related to all of that. So you have to account for that. Okay, so this fudge factor, R, which comes up in so many other places, this R thing. It comes up a lot in physics and in physical chemistry. So this R, and we will solve problems with PV equals nRT in a minute. When you're solving problems, look at the units that you have. And based on the units that you have, pick a convenient R. It's a fudge factor. It doesn't matter, it doesn't have any meaning. It's just a fudge factor. So if I happen to work with, someone told me I want my final volume in meters cubed, well, then I'll use this. It's convenient. I already have it in meters cubed. I might as well do that instead of just converting stuff, right? So you just look at the problem statement, look at the units that they give you, and try to make your life easier. That's all. And so these are the most common ones you'll use. You can use 8.314, 0.08206, or 62.36. These will all give you things based on these units. I did not give you the imperial one. It exists as well. You can go look that up. I will not encourage you to use imperial units in this course. If you take engineering courses later on as a junior or as a senior in lab, they very often have you use these.